Hello friends! So today we're taking a deep dive into parsing, and for that I need to introduce you to a very important concept called grammars. Remember the last time we talked about the compiler pipeline? So here's an example of a very simple classical pipeline. It can of course get more complicated with virtual machine and just-in-time compilers. Parsing though is going to be pretty much the same for any scenario. It's going to be a big part of what we focus on in this course. So you'll remember from last time that lexing or tokenization is going from the input, which is basically just an array of characters, into an array of tokens, which are the minimum non-divisible unit. Parsing, on the other hand, is going from these tokens into a syntax tree that gives meaning. So instead of being just a sequence of units, it becomes a tree that gives meaning. You have the example of assignment that we saw last time here. Okay, so let me give some definitions. A grammar is the formal definition of a language. Formal here means mathematical, it means it's precise. It's not like when you're going to describe a language to your pal. Here, it has to be precise so it can be interpreted by a computer. What's a language then? A language is a potentially infinite set of sentences. So it's a set here in the mathematical sense. What is a sentence? Well, a sentence is going to be conversely anything that's in a language. So if you take a programming language, a sentence is going to be typically a source file. Or if you have a read, eval, print loop, it's going to be an expression that you can type in there, and that can be parsed as one thing. If you go into language theory, there's also the notion of an alphabet, and that's basically just the set of tokens that we have in your language. Something I didn't say on the last slide as well is that sometimes parsing and lexing are done together as a single big parsing step, so lexing is optional. Okay, so we're going to focus on this example for most of our introduction to parsing, and the example will be the grammar of JSON. So JSON is the JavaScript object notation. It's a very popular format to store data and configurations. So what's the grammar of JSON? So basically, what you will parse if you parse JSON is you're going to parse a JSON value. Okay, a JSON value can be a string literal. So version here is a string literal. It can be a number, 17. It can be an object. So an object is a series of pairs that are going to be bracketed by braces. So you can see all of these lines here, object, and the whole thing here is an object too. So we have a syntax for pairs, right? So that's here, you can see that these objects have a single pair, and the big object has two pair, one here and one here. And finally, an array. So the value of bundles here is the array that contains all these small objects. This is a simplified grammar, so the real JSON also has like no true, false. I think that's all I left off here. So it's almost the real thing. Another thing that's not represented here is the syntax of tokens. So I've highlighted here in red everything that pertains to the lexical part. And we will talk in length about lexing a bit later. But for now, we'll focus on parsing, so we'll assume that we can recognize these tokens. So they're given to us, we just work on tokens, we don't do lexing now. Okay, so in this grammar, you see that we have a series of definitions. The thing on the left, the thing being defined, are called non-terminals, while the tokens are being called terminals. So these are terms from the formal theory of languages. You can see how these terms make sense, right? A non-terminal is something that has a definition, a terminal is a thing that is given, it has no definition. And we'll expand on these terms when we talk about context-free grammars a little bit more. So, yes, so you see that in this definition in this notation for the grammar, we have used some specific notations which I have highlighted in red. So we have choices. So a value can be a string literal, it can be a number, it can be an object or an array. This is a choice. An object then needs to have the braces. This is not negotiable, but it can have no pair at all. So you see that there are a pair of parents there, and the interrogation sign means this is optional. The star here means that everything that is under braces here can appear 0 or more times. So basically, you have pairs are separated by commas, and you can have 0 pairs or you can have many pairs. You're probably familiar with this notation because it's the same notation that's being used for regular expressions. And I think most of you must have used regular expressions at some point, so this should not be too unfamiliar. Now this notation, I've called it the parsing expression grammar notation. I could have called it the regular expression notation, but here it's used for a grammar, not just a regular expression. We'll see how grammar and regular expression relate together a bit later. But for now, let's call it a parsing expression grammar, and we will explain exactly what it is in a bit. So another notation that's very popular is the extended Bacchus-Nor form. Bacchus and Nor are these guys, and they're famous for their work on Fortran and COBOL, so very old programming languages. What you can see here is that for optionality, we use brackets. So everything between brackets is optional, and everything between braces can appear 1 or more times. So to go back to here, right, where we had like 0 or more, well, here we need to combine 1 or more with optional, which comes down to 0 or more. Otherwise, it's exactly the same. Okay. So this is extended Bacchus-Nor form, which is an extended version of the Bacchus-Nor form. In Bacchus-Nor form, these symbols do not exist. This optional 1 or more, they do not exist. So how do we do? Well, we use recursions and a lot more rules. So let's take the object rule. It's here. So instead of having like this whole affair here, what we end up doing is that we define a new rule called pairs. And pairs is optional, which means it can match epsilon. Epsilon means nothing. Just, it doesn't match anything. I could have used an empty pairs of quotes there, but epsilon is the usual mathematical notation for this. Or it is actually some pairs. And some pairs is going to be a pair, and then t pairs, which is a recursive expression, which can be either nothing, or a colon followed by more pairs. So you see that there's a recursion there. This goes back here. So this is obviously less clear, but this is the original notation. And to be honest, there is some value in this notation. If you're going to define the semantic of a grammar, because so far we only have a grammar that is a description, but we haven't really said what this notation means. This will come later. But it's easier to assign meaning to rules that are as simple as possible, so they don't have all this stuff here, because you need to define the meaning of that too. So the simpler it is, the easier it is to define meaning. And actually, the way grammar formalism are typically defined, it goes even simpler than this, because you don't have the choices. Basically, instead of having, for instance, t pairs is epsilon, or a colon then pairs, it will be t. You have two definitions for t pairs. One definition for t pairs that says it can be empty, and another definition for t pairs that says it can be a colon followed by pairs. Okay, so now we come to the grammar formalism I was talking to you about. So parsing expression grammars, PEG, is a grammar formalism, and it's also a notation. What's a formalism? It's a mathematical system to define a language. So remember, the language is a set of sentences, a mathematical set. And a notation is a way to denote, to describe the grammar. And this grammar that has been written using the notation will be interpreted by the formalism. And here we mean, by interpreted, we mean that the formalism will give meaning to the grammar by basically saying, okay, we have this description. Here is the language, the set of sentences that this grammar denotes. Okay, so formalism is a way to go from notation to the set of sentences, the language. So traditionally, well, the PEG notation is used for parsing expression grammars. That's one formalism. Another formalism that's even more popular is context-free grammars. We will talk a lot about them in this course. And traditionally, the Backus-Naur notation, the Backus-Naur form, is used to denote context-free grammars. CFG and PEG are similar, but they are different. This is very important, and we'll repeat that later. Indeed, it's the next slide. So CFG and PEG are different formalism. And that trick with the example I took is that the JSON example is very simple. And for them, actually, the PEG and CFG grammars, they look more or less the same. So basically, the semantics are different, but the result of applying them on the grammar is the same. This is not true in general. There are very important differences between CFG and PEG, and we will explain them later in the course. Right now, we're just doing a light introduction. I think there's already enough concept floating around to confuse it further, but keep in mind for the rest of the course, CFG and PEG are not identical, they're different. So I said EBNF is usually a notation for CFG, and the PEG notation is usually for PEGs. The thing is, it's just a notation, it's just a matter of convention, okay? So as long as you define a way to map the notation to the formalism, you can use any notation you want. You just need to say what it is you mean by your notation, okay? And you can invent new notation, etc. That's not the point of the course, but I sometimes see people arguing very strongly about, oh, you use this symbol and that's for this formalism. Well, no, it's just if I say that this means this, I can use it. I can use anything I want as long as I define it, as long as it's clear what is meant by the symbols that I'm using. Okay, so what I'm presenting to you is convention, but this is computer science. You can do whatever you want. Okay, so this was a bit of a dense theory segment. Next time, I'll give you some background on parsers, and we'll see that a parser is not a grammar, and we'll learn all about that.